So welcome everyone to this second part of the fourth webinar. The second part today is on probabilistic modeling to make better use of quantitative information from in vitro assays and taking into account uncertainty. So here is a very brief recap of the webinars in that series for the WNT that have been held so far. In June, we had the webinar on extracting the essential information and principle of validation and good in vitro method practice for NAMs. We had a few key points that are listed here that were mentioned during the webinar. Later, we had a webinar for ecotoxicology, new methods and approaches for cross-species extrapolations. And again, a few of the key concepts, keywords that were brought in the webinar. Then at the end of August, we had a webinar on scientific and test method readiness of emerging technologies, criteria, examples, and experience. Again, with a number of concepts and important aspects to consider. And last week, we had the fourth webinar, part one, dealing with reproducibility issues from a more technical perspective, maybe. In toxicological studies, we talked about not only in vitro, but also in vivo studies and how this variability and the reproducibility issues affect the emergence of new approach methods. And the concepts that were brought to the webinar related to point estimate in animal studies, to margin of uncertainty determination and analysis of variance. In relation to the predictive capacity of alternative methods, we heard that it's important to set reasonable expectations for evaluating in vitro, in silico methods based on the inherent variability in animal studies. In relation to the technical reproducibility of in vitro methods, we heard that it's important to have transparent protocol description, transparent reporting of results as well. And the targets here for improving that are certainly research, funding agencies, editors, and publishers. These certainly could largely improve the credibility of NAMs data and their uptake for regulatory use. So today, we will be having the second part of this webinar on reproducibility issues. And as much as method developers and risk assessors would like clean and highly reproducible data, variability and uncertainty generated are intrinsic components of any model, animal model or not. And the possibility of expressing variability in an easy to understand dimension is certainly one step towards more comfort and better acceptance of this uncertainty. So in many ongoing projects, as we have seen, identification, characterization, and expression of uncertainty is an important in the process developing new approach methods. So this is the program for today. We have three speakers. I'll introduce them very briefly. Thomas Hartung is steering the revolution in toxicology towards organoid cultures and use of artificial intelligence as a professor at the Johns Hopkins University Center for Alternatives to Animal Testing. Then we will have Weishue Chiu, who is a quantitative risk scientist with experience in all aspects of human health risk assessment, data integration across disciplines, to provide quantitative estimates of risk. He's professor at Texas A&M University at the Department of Veterinary Integrative Bioscience. And our third speaker today is a mathematical modeler at Unilever, Joe Reynolds. His key area of expertise include Bayesian inference, mathematical modeling, and uncertainty quantification. He's also involved in the project on defined approaches on skin sensitization for risk assessment. So without further ado, we'll move to our first speaker. Thomas, the floor is yours.
Thank you very much. I now consider myself officially recognized by the OECD for steering a revolution, which is something new. Thanks a lot for doing this. Yeah, I'm steering a revolution. I hope for a revolution, a scientific revolution, a paradigm change. You mentioned that I'm directing a Center for Alternatives to Animal Testing, but most of all, I'm a physician in the leading school of public health, and I believe very much what was printed on these masks, actually saving more than animals. What we do is for the benefit of patients and consumers. The topic of today, probabilistic risk assessment, is one which is close to my heart for some years now, and a lot of current activities are centered around this. I made my slides available, but I also have a couple of articles lodged with some QR codes. I will show the QR code at the very end, again, if somebody's interested in these. I should announce a few conflicts of interest, but it will be short. Just take everything with a grain of salt. I'm invested in several activities to bring alternative approaches to use the rubber on the ground. That's the problem. The problem is that as toxicologists, we love it simple. We love it black and white. A substance is toxic or non-toxic, and then we want to close the books. The reality is different. The reality is a lot of shades of gray. And these shades of gray depend on circumstances, on use scenarios, and so on. And it is all about a probability of something. The advantage of black and white is we can close the books, but then we need a definitive test. And that is what your program is all about, defining definitive tests, which are difficult to replace, as I have endured in my time heading the European Center for Validation of Alternative Methods and others trying to get alternative methods accepted. Because every new test is a game changer, because it will not have exactly the same results. And this is what both the regulatory side and the regulated community fear. If we embrace that everything is full of uncertainty and it is full of probabilities to have a certain effect and a certain risk, this requires continued surveillance, adaptation to progress. No test is definitive. But on the good side, I think it is better to have something which is not a game changer, but a game shifter, because every new evidence can then only be seen as something which is shifting our assessments, changing probabilities and uncertainties. I had the privilege to be invited 3 years ago by the Department of Defense in the US to put together a team, and Weishue, who is is giving the next talk here, and Ana Navas-Sien from Colombia joined for this effort. And we put together a team of about 30 people to think about the future of toxicology. And this is in the end a call for a human exposome project, so putting really chemicals and other types of exposures in front. This will soon be available, probably next month, through the Department of Defense. I'm putting this up because we had 3 pillars here. We said we need to be more exposure driven, We have to embrace technologies like microphysiological systems, AI, high throughput testing, all the omics technologies, which were not yet part of the infamous TOX21 report. But very importantly, we need to find ways to integrate these evidences. And one of the key recommendations here was to embrace probabilistic risk assessment. So it is part of a larger framework to rethink how we are doing risk assessments, and I invite you to put some attention to this. So the challenge is really the data integration, because what we are all witnessing is that we have one standard test, a guideline test, which we rely on and which we use in different sectors. We are seeing that we have more and more challenges to integrate evidences. And this is the same whether it is a systematic review, which is becoming more and more popular, whether it's a regular risk assessment of a complex set of information, or whether these are integrated testing strategies. You like to call them integrated approaches to testing and assessment, IATA, or defined approaches. In all of these cases, it is about putting things together which are somehow trying to complement each other. To talk a bit very quickly on the systematic review side, the evidence-based approaches, we started activities towards evidence-based toxicology in 2006 out of ECVAM, had the first conference in 2007. I have a chair for evidence-based toxicology since 2009, and we handle the evidence-based toxicology collaborations secretariat since 2011. And organizations like the EPA, the FDA, the European Food Safety Authority are part of the board of trustees here, for example. And we have interacted with about 1,000 people since 2011. So it's really a very increasingly active field. Why I'm putting this up is because evidence-based medicine, which is the role model for this, is based on principles which are very closely linked to probability. This is one of Hopkins' iconic figures. He said already 100 years ago, medicine is a science of uncertainty and an art of probability. In the evidence-based medicine field, we read it like this: evidence-based medicine, a science of uncertainty and an art of probability. And you know that evidence-based medicine is driven by the Cochrane collaboration. And if you just look into the symbol of the collaboration, this is actually probabilities. These are the odd ratios, a forest plot of probabilities, which is used in meta-analysis to combine information. So it is really about trying to aim to put a little bit diverse information together through probabilities. And just to show you how this is increasing, this is the number of systematic reviews which took place. The key tool of evidence-based toxicology, since we started here in the early 2000s, it is really exploding, and and this is more and more daily practice for many of us. The second element, the integrated testing strategies, the IATAs and defined approaches, this is also something which is changing the face of toxicology and is the necessary consequence of using more of the mechanistic assays in vitro assays. This is a recent overview article. I called it in vivitrosi, in vivo, in vitro, and in silico combined. And just to tell you, this is a key problem to really take advantage of the variety of approaches which we have now at hand. And I believe very strongly that the prime opportunity in integrating evidence lies in using artificial intelligence. Because artificial intelligence is exactly this. It is able and is shining when we have diverse data sets which have to be combined. It is not better than descriptive approaches if you have only one type of data. And in toxicology, we have tons of big data now. Not only the databases of legacy data, the internet data, there's 900,000 safety data sheets on the internet, the literature, there's 1 million publications in PubMed alone every year, and 80% of them describe substance effects. We have sensors, we have robotized testing, we have the omics technologies producing gigabyte of data, we have high content imaging, digital pathology, and others. All of these are feeding data which we need to integrate and interpret. Our own work in 2018 gave an example of how artificial intelligence can use traditional data sources, the legacy data of the past. At the time, 10 million structures were used to create a proximity web of things. And I say we, this was mainly done by Tom Lichtefeld, who is now a junior professor and a research associate in my group at the time of his PhD. I will be very short here. The publication in 2018 showed that for 190,000 chemicals where there was a classification done, actually the software was able to predict this correctly 87% of the time, which outperformed the reproducibility of these animal tests, which was on average only 81%. So it did exactly what a good toxicologist is doing, which is being better than the animal test at hand and taking a lot of additional information into account. And this was covered in Nature and Science twice. So there was really a lot of attention given to this thing. And I'm putting this out not only because it is, in the meantime, a tool available, which has actually been accepted in the chemical legislation in Australia already, but I'm putting this out especially because it is, I think, an approach which can be expanded. We showed in a paper in 2020 that the very early version of the program was very good in predicting human skin desensitization, not only the animal data like the 2018 publication. You see 80% roughly. The local lymph node assay predicted these human data, type of human data, only 74% of the time. So it is better than the animal test in predicting the human outcome in two different data sets. You also can run it on tons of data. A publication coming out next month will show how we applied this method for almost 5,000 food relevant substances in the US. And in 1 hour, this calculated the equivalent of 38,000 animal studies worth $250 million. So it is a tool to help assess large data gaps, which we unfortunately have in many areas of risk assessment. And the paper we are just preparing is showing that this can also be applied to both systemic toxicities. You see data here for reproductive toxicity, predicting 1,100 substances, 82% accurately, and predicting carcinogenicity, 75% accurately for 950 substances. This is not yet really optimized, not yet validated really fully, but this is something which shows the promise of these technologies also for more complex endpoints. And also quite interesting, these are data on in vitro assays from the TOX21 battery of tests. And you can see how well estrogenic and androgenic effects have been predicted based on the large data sets available from the TOX21 collaboration in the US. I think there's a lot of promise. And there's at the moment an EU project I'm strongly involved with, which is the OnTox project, which is trying to put this approach towards liver, kidney, and the developing brain. I think there's a lot to be expected. The limit is the sky in developing a tool which should be part of the toolbox in order to help us. But the important thing in the context of our work here is this way of transfer learning data fusion outputs probabilities. It tells us something, what is the probability of the hazard it predicts. And for this reason, it is feeding directly into assessments which are based on probability. And this is something really unique of this approach. It really says for each and every prediction, this is 85% certain, this is 90% certain, then you can decide whether this is enough to take a decision, whether you want dedicated testing, whether it's good enough for a household cleaner or good enough for baby food. So really different requirements with respect to the probability you want to see. We have summarized in this article earlier this year the state of the art of probabilistic risk assessment. And I put up the keystone for the future of toxicology because I strongly believe this. It is summarizing activities which were last strongly proposed by the US EPA around 2014, which are used in some fields of risk assessment, but which are not the common approach, propagating the uncertainties and showing what the consequence is for an individual or for a population. So probabilistic approach is a very common uncertainty analysis in most fields of engineering. Instead of measuring or measuring exactly the size of these two shapes, you can simply find out by randomly letting these balls fall. How many balls are falling is depending on the surface, and you can evaluate this in a simple experiment by resampling your balls in this case. This is essentially the Monte Carlo type of assessments, which is typical. And you can combine quite easily several probability distributions to a new one. Let's say you have one for exposure and you have one for the sensitivity of individuals. You can overlay these. And this is the propagation of variability and uncertainty which we are aiming for. Within the ONTOX project, we are interested in combining exposure and risk based on probability. And this is easy on the exposure side because a lot of this is based on distributions already. And a lot of probabilistic methods like the pharmacokinetic-based, physiology-based pharmacokinetic modeling, PBK, are probabilistic technologies. So probability of exposure is relatively easy. Where we are, and we are also including some thresholds of toxicological concern, actually, again, a method which is based on a distribution of no effect levels. I don't go into the details of TTC in interest of time, but this is a very interesting concept on its own, which is, as I said, based on probability distributions. But now the challenge for the ONTOX project is really to develop a concept of probability of hazard. And we're doing this here by using the approach I've been mentioning, the RASA approach of coming from chemical structures and the properties known, and combining this with what we call ontologies, which is essentially an adverse outcome pathway driven framework where we take the perturbation of certain pathways and want to translate this into what does it mean for probability of hazard. And then these shall be combined to a probability of risk, where we hope that minimal risk can lead us to, let's say, putting on the back burner a substance, risk management if there's a high probability of risk, and perhaps then giving advice for more testing, where interestingly these methods can be applied backward, where you can, for example, calculate how probable is a change in the overall assessment if I invest in this additional study and it has this or that outcome. So information economics is an interesting way of saying it simply does not serve us anymore to run a cancer bioassay or whatever. It will not change really the outcome. We held a workshop on probabilistic risk assessment in July this year in Italy. The workshop report is in preparation. This is, by the way, a picture we borrowed from the EPA's and activities in 2014. And with this, I would like to leave you for my co-speakers, citing Cicero, who already said, before Christ, probability is the very guide of life, and I hope it will become the very guide of toxicology. Thank you very much.
Thank you very much, Thomas, for this high-level, comprehensive, but solid overview of probabilistic risk assessment and ongoing projects and sharing also a lot of resources and publications. I think that's very useful. As I said in previous webinars, all the presentations will be uploaded on the WNT community site, as well as the recording of this webinar today. So yeah, thank you. We move to the next speaker, who is Weishue.
Hi there, how's the sound? Is everything all right?
Works well, yeah.
All right, so you should see the slides now, correct?
Yes, we can see the slides. Thanks.
Okay, great. So thanks, Thomas, for that great overview. I'm going to dive in a little bit more detail on the risk assessment side. First, I wanted to acknowledge all the people who've contributed to all the work that I would be presenting. There's a WHO group that I was part of for about 8 years, and then a lot of other colleagues that I've worked with. Our funding, of course, and I do work as a consultant for a company trying to commercialize the Bayesian benchmark dose modeling system. So, the current non-probabilistic risk assessment is, fairly simple and crude in that you first either find a low AL or a no AL, hopefully a no AL, you divide by some factors, and then you get a reference dose. But, this really, as Thomas alluded, leads to, a sort of false sense of security. First, at the no AL, you don't really know what the size of the potential effect is, depending on the variation, the degree of variance in the study. It could be very large or it could be very, very small. These factors that we divide by, they're assumed to be conservative, but there's not really a lot of evidence as to how conservative they actually are. And because of that, it's unclear when we get to a final reference value, how conservative it actually is. Different assessments will likely vary greatly in the degree of conservatism and how safe they are. And then additionally, there's no estimate of any type of residual risk. We have this sort of bright line between safe and unsafe, whereas we all know everything, the degree of toxicity is a continuum as you increase in dose. So the WHO, we have a WHO working group that developed this new approach to go sort of beyond the RFD type of concept to what we call the target human dose. And the basic concept is here, where we have, we can see that different individuals have their own sort of personal dose response curves. So more sensitive individuals are more to the left, more resistant individuals are more to the right. And then we can define, for a particular magnitude of effect, the dose at which, say, the 1 percentile experiences that magnitude of effect. And that's the human dose for, in this case, a magnitude of effect of 10 of whatever units are in 1% of the population. And then we can define sort of a confidence range as well. And so in this way, we have a clear idea as to what our actual target is. And as opposed to just having a very vague notion as to safe versus unsafe. And of course, these are actually more risk management decisions as to what magnitude of effect is acceptable and what incidence in the population, residual incidence is acceptable, as well as the level of confidence that we are willing to accept. So what we did is to try to make this a very analogous approach to the RFD, basically replacing NOALs with benchmark dose estimates, which are inherently have distributions, and then these dosimetric adjustment factors, these uncertainty factors, each of which are replaced by distributions, but these distributions are informed from historical data across species, across different chemicals, and thereby we replacing these sort of fixed factors with data-derived distributions that are based on our prior knowledge of chemical toxicity and variability. And then these can be combined probabilistically, as Thomas showed. In our particular approach, we have two. One is a log normal approximation, and one is just straight Monte Carlo simulation. And then the lower bound of this confidence interval can be thought of as sort of a probabilistic version of the reference dose. So it can serve kind of the existing risk or decision context that the reference dose does, but it's derived more rigorously using distributions that account for the degree of uncertainty. And we've demonstrated that this is feasible for that almost any reference dose can be, can be recalculated as this HDMI concept. We took over 3,000 peer-reviewed toxicity values, just looked at oral reference doses based on animal data, and that there was sufficient reporting of what species, the point of departure, et cetera. We ended up for about 600 chemicals, almost 1,500 reference doses that we recalculated using probabilistic methods, and these are a whole variety of effect types that are the basis of the points of departure. And from this, we not only can generate sort of these probabilistic versions of the reference dose, we can actually generate dose response functions. So, this here is the upper bound, this is the median estimate, and this is the lower confidence bound for the dose response functions for each of the 16 or 1,500 different dose response data sets for 600 chemicals. And what we found, and this is comparing, say, to the traditional reference dose, the deterministic one, we found that, under our paradigm, the traditional reference dose has an upper bound risk of typically a few percent, but in some cases, you can see here, much higher. The median and lower bound risk were mostly very small, although there's a few here that poke up into the few percent range. And then we could also calculate, say, an expected value if you wanted to do economic benefits cost analysis, say. The benefits of this approach is that, they address first a number of the limitations in terms of the transparency of traditional risk assessments, which are really just based on, fixed factors. You derive something that you can actually interpret in terms of severity of effect, incidence of effect, and then confidence in terms of statistical confidence. You can still generate a point estimate that you can use in a traditional bright line approach, but you also can derive these intake response functions that then you can use to inform trade-offs and benefit cost type analyses. And this has, we've demonstrated they can be readily implemented with experimental animal toxicity data. So with that as a backdrop, I'm going to move now more to in vitro data. And I'm taking a study by Richard Judson from more than 10 years ago, in which this very same approach essentially was applicable to high throughput in vitro assays. So basically taking a bunch of assays, you have a distribution of biological pathway activating concentrations. For toxicokinetics, you convert those concentrations probabilistically to oral doses, and then you have a distribution from which you can take a lower confidence bound as a point estimate, but you still retain this information about the uncertainty and variability. So in this particular case, uncertainty and variability are kind of mixed together, but we can actually disaggregate that, and I'll get into that in a moment. So, recent efforts at all this sort of risk prioritization, looking at oral equivalent doses comparing to exposure estimates, these are all inherently probabilistic in terms of looking at across the different types of high throughput assays. Exposure estimates are very difficult to do precisely, and they span, the uncertainty can span many orders of magnitude, but we can still do a good prioritization in terms of looking at those chemicals for which there's a small margin versus a larger margin having a greater priority than those with a larger margin. So with that, I wanted to dig a little bit more deeply into some of the research that I've been doing with my colleagues on population variability, as opposed to just looking at uncertainty. So variability and susceptibility remains a really large challenge in risk assessment, whether it's from in vivo data, where we use single inbred strains of mice, whether it's from in vitro data, where almost all of the data is based on either immortalized cell lines or single primary cells from a small number of donors, or other types of cell banks that are really just single genetic backgrounds. And even the PBPK models are often done in sort of a single individual kind of approach, in which we're really just converting to first some sort of average human, but we really want to make predictions for a highly variable population. And so that's where the limitations of these sort of single genetic background approaches comes into being. And our current approach for dealing with this is really just counting how many fingers we have, assuming that safety factor that is equal to the number of fingers we have is protective for the sensitive part of the population. And then if we want to get really sophisticated, we divide that factor of 10 into square root of 10 and times the square root of 10, where we have two factors of 3.16 for each for toxicokinetics and toxodynamics. And this seems a bit pedestrian given the much greater availability of data, particularly since the genetic, the sequence in the human genome and genetic revolution, there must be a better way to address this. And so, there are a number of population-based approaches and tools that are available. Actually, at Eurotox ICT, I just gave a talk talking about the diverse mouse populations in vivo. But so today, given the audience, I'm going to talk more about using populations of human cells in vitros. So we do have both cell lines as well as induced pluripotent stem cells that we've used, and this involves studying these effects in a population context as opposed to an individual context. So as an example for the in vitro for the cell line, where we use lymphoblast cells from the 1,000 Genomes Project, where there's genetically diverse populations that have all been sequenced from across the globe. We put that into in vitro model system, use high throughput testing, and this was actually done with robots at NCATS. But to analyze this data, because there's both intra and inter-individual variability in these dose response curves, we used a hierarchical Bayesian approach in which we have a basic, Hill function for the dose response curve at the individual level, but we also we recognize that the parameters of that model vary in the population, and so we basically have a random effects type of model, but using a Bayesian approach. So just as an example, here for one chemical, we have the gray lines are the individual concentration response curves, and then the fit for both the posterior median, the population median, as well as the fit, the 95th percentiles are shown here. And then for the EC10 value, where 10% change in response, this is the distribution across individuals of the EC10. And then we basically consider the ratio between the median individual and the 1 percentile individual as sort of a toxodynamic variability factor that we would use to replace the default factor of 3.16 for toxodynamics. And so we did this for about 1,000 individuals, about 170 compounds, and we definitely found a high degree of chemical to chemical variation in the degree of population variability. Some chemicals had very low amounts of variability, about 2-fold, and then some had large, almost 10-fold variability between sort of the median and the more sensitive part of the population. And so, so I mentioned this toxodynamic variability factor that we were defining as a replacement for the default uncertainty factor is meant to be a factor that protects up to the most sensitive 1% of the population. For some validation, we looked at the available vivo data on population variability, which was only available for about 40-some chemicals. And this was data that was collected over many years by Dale Haddis, and that's the black line here. So for the cumulative distribution of the fraction of compounds with different factors, variability factors for the 1%, for protecting the first percentile. And then the red here is our estimate based on our Bayesian analysis. And this includes shrinkage due to the intra-individual variability. So it's very similar distribution. In vivo values probably include measurement error because these were just all based on point estimates, and so there's no shrinkage there. So it's not surprising that they're slightly larger, but you definitely get a similar range of variability across chemicals in the degree of population variability. Now we've also moved to looking at induced pluripotent stem cell derived cardiomyocytes, in which again we have a population of donors. In this case, we could only get about 40. I won't go into the sort of details as to why cardiomyocytes are a great thing, but they've really been used a lot in the pharmaceutical realm to look at cardiotoxicity screening. But for about 40 individuals, about 130 different chemicals, we again applied this Bayesian concentration response modeling approach to look at both the hazard and the risk characterization. And in this case, in addition, not just cytotoxicity, but we have different types of cardiotoxic endpoints, including positive and negative chronotropy, increasing or decreasing the beat rate, as well as a surrogate for QT prolongation, which is a very important arrhythmia, particularly for pharmaceutical liabilities, and then asystole and cytotoxicity, other types of more severe endpoints. And again, we get these toxodynamic variability factors that are consistent if you look at the more severe endpoints of cytotoxicity here and asystole. And these were the data I showed before. This is the in vivo. This was the cytotoxicity from the lymphoblastoid cells. And you get around, on average, about the 3.16, but there's definitely a long tail of values that some chemicals have a large degree of population variability. Now, if you look at functional phenotypes, so this is QT prolongation and then positive and negative chronotropy, you get larger degrees of variation. There's less chemical to chemical variation here, so that's why with the shrinkage you get less information about population variability, just because we're limited in terms of the noise that we have in the data. But it's clear that on average, functional phenotypes for cardiomyocytes actually have larger degree of population variability than cytotoxicity. So this implies that as we look across chemicals as well as across different endpoints, there's likely to be a wide range of differences in the actual degree of population susceptibility or variation in population susceptibility on a very chemical and endpoint specific basis. Now we push this further as well, looking at risk characterization, looking at this margin of safety or margin of exposure. This is for the drugs over here, and this is for environmental chemicals. And then where these little distributions over here on the left are the exposure distributions, and on the right is the hazard, the toxicity. So in over half of the pharmaceuticals had margins of exposure of less than 100, meaning that there is, there's a potential liability there, and that we actually knew this because we picked a number of the chemicals so that we knew that they would have that they've been known to have some QT prolongation, for instance, liability in the clinic. And then, fortunately, only one of the environmental chemicals out of these 100, well, there's only a few dozen for which we had exposure estimates. Only one of them had a margin of exposure below 1,000. So, in this case, for at least this set of chemicals, for this set of toxicity, the bad news was that there was hazard for a number of these chemicals, but the good news was that it doesn't appear like, at least at current exposure levels, there's a substantial level of risk. So if we go go back to the big picture a little bit and look at evolution of probabilistic approaches. So we have our traditional NOEL divided by a number of fixed factors approach. There's been moved towards benchmark dose-based approaches, which is just replacing the NOEL with a benchmark dose, which is essentially a distribution we're taking the lower confidence bound. But if we abstract to a probabilistic conceptual model, we essentially always have some test system in which you define a point of departure. We need to extrapolate the test system to some typical human, and then we need to address human variability, population variability, in order to be protective of a sensitive human. And each of these can be represented by a distribution rather than a fixed factor. And so these probabilistic inputs, whether it's in vivo data, whether it's in vitro data, whether it's in silico data, they should all be expressed, or all can be expressed in terms of an uncertainty distribution in which you combine to get your final toxicity value that for which you define both the degree of uncertainty you're willing to accept in a particular context, as well as the amount, in terms of the variability, how much of the population you need to protect in your particular decision context. So I'm not going to go through this slide, but I'll leave this since the slides will become available. This is sort of what I conceive of as a unified probabilistic toxicity value framework, in which you can start at any of these different places depending on what type of data you have, whether it's human epi data or whether it's in vitro data, and then each of the extrapolations or conversions as well can be informed by both traditional data or NAM-based in vitro or in silico data. And so in the end, all your inputs should have their uncertainty quantified. And then when we get a toxicity value protective of sensitive individuals, we also have our aggregated uncertainty there. So just to end with some key messages, Traditional deterministic dose response estimates are problematic for a number of reasons that Thomas went through quite thoroughly. Probabilistic dose response assessment allows one to quantitatively incorporate both uncertainty and variability by redefining this reference dose concept as this HDMI. And then it also enables more sophisticated decision-making in terms of looking at risk-risk trade-offs and benefit-cost analyses. And these probabilistic approaches can be applied no matter what type of inputs you have, in vivo, in vitro, in silico, and whether it's deriving points of departure, whether it's looking at interspecies or intraspecies variability, or whether it's doing in vitro to in vivo extrapolation. So with that, thank you very much. And sorry, I think I went a minute or two over, but hopefully we're still on time.
No problem, Weishue. Thank you very much for your presentation. It certainly gives reassurance that variability, even in vitro assays that are sometimes, as we see more often, based on the primary human-derived system, this variability is overall indicative of population diversity, and that there are methods out there, statistical approaches that to integrate that evidence and determine probability of effects. So we'll move then to our next speaker, Joe Reynolds.
Hi, thank you, Anne. So just a very quick introduction about me. So my name is Joe Reynolds. I work for Unilever as a computational toxicologist. I have a background in mathematics, and my area of speciality is Bayesian statistics, which we use as a tool to quantify uncertainties for decision-making frameworks for risk assessments at Unilever. Today I'm going to talk about a particular risk assessment tool that has been developed by myself and various colleagues at Unilever. And this tool is aimed at quantifying skin sensitization risk. And specifically, it's designed such that you can use AOP-aligned NAMs and new approach methodologies to do that. So what does Unilever care about? So Unilever is a very large company, 55,000 employees, and makes a number of products which we market to consumers. A subset of those products are cosmetics, so shampoos, face creams, etc. And SEAC, which is the building I work in, they are interested in essentially answering a very simple question, which is it safe to include a certain ingredient in a product at a certain percentage, given that the products will be used in, under some particular exposure scenario. And so the risk assessments for that is exposure driven. First, you care about how much of the products the consumer is going to be exposed to. You care about how much of the chemical, you care about how much the percentage in the product that the chemical is going to be in at, and therefore you also need to know some notion of the hazard of that chemical before you can conclude on risk. One of the endpoints that Unilever is particularly concerned with is skin sensitization. So this slide presents the adverse outcome pathway of skin sensitization. So typically some chemicals are electrophilic, and this means they can bind covalently to proteins in the skin following exposure. And this binding will haptenate a particular peptide, which then may be presented by keratinocytes and recognized as a foreign body by dendritic cells, who then may migrate to a lymph node and result and cause T cell activation. And the problem with this is then subsequent exposure to the same chemical can initiate an immune response, resulting in atopic contact dermatitis. So Unilever cannot get away from using electrophilic chemicals. So common chemicals that might be electrophilic includes, for example, preservatives, which are required by law to be in certain products, or you may need examples of the chemicals, the common chemicals are fragrances, which are obviously a big selling point of the products. And therefore, the risk assessment for electrophilic chemicals is really concerned with their inclusion levels in the product and managing those such that the risk of inducing skin sensitization is low. Historically, the risk assessment of skin sensitization has been conducted using animal tests, particularly the local lymph node assay more recently, and before that, the guinea pig maximization test. There are existing human studies. So these are typically run by fragrance houses to demonstrate that at a particular exposure, you do not get skin sensitization from a particular exposure to a particular ingredient. But more recently, a number of new approach methodologies have been developed, and these are aligned with various key events within the antivirus outcome pathway. So when we're talking about key event one, which is the notion of whether the chemical can react with protein, NAMs such as a direct peptide reactivity assay or the kinetic version of that, the KDPRA. These are experimental in vitro tests aimed to essentially measure reactivity. And of course, as you go up the AOP for the key events, there are a number of different NAMs aligned with those as well. So for current risk assessment Unilever, we want to only consider NAMs for making a risk assessment conclusion for a particular product. One of the tools we've developed to do this at Unilever is called the SARA model. So SARA stands for Skin Allergy Risk Assessment. And an early version of this model was published in 2019, and an updated version of this model was published this year. Essentially, the SARA model is a Bayesian statistical model. So it uses Bayesian statistics to describe the relationships and the variability of data from a number of NAMs and historical study types, such as local lymph node assay and HRAPT. Effectively, it is a probability distribution, a very high dimensional probability distribution, which is built up through many assumptions around the relationships between individual variables. So, for example, one of the assumptions pertains to variability of observations in the DPRA. Or there will be model structure to describe variability of the local lymph node assay results, for example. To go into more examples of how this is okay. So before we get to how the model is built, the key quantity of interest we would like from the model is a notion of potency, which is human relevant. So the HRAPT is a clinical study in which a cohort of individuals, typically 100 people, are exposed to a chemical repeatedly. A little bit of time has elapsed, and then they are subsequently patch tested to assess onset of contact allergy. We have introduced some notion of the HRAPT 1% sensitization dose. And so this will be a dose in a HRAPT for a particular chemical that has a risk of inducing sensitization of around 1%. Now this thing we call ED01, and we posit that this is a useful quantity of interest from which to establish a risk assessment. So the types of data that we use in the model are obviously HRIPTs. So we want to benchmark that value. We want to use HRIPTs to work out what that value looks like for a number of chemicals. And of course, we also have historical local lymph node assay data in there, and then a number of NAMs. Particularly, the choice of NAMs is a historical consequence of what was published in the Cosmetics Europe database a number of years ago now, but includes specifically the DPRA, which, as I say, as just said before, is a measure of depletion of cysteine and lysine peptides with an in vitro test system. The keratinescens assay, which is a measure of luciferase induction, and the H-clat and U-sens assays, which can be considered Me-Too assays, and they're aligned with key event 3 in the AOP. They measure increased expression of the CD86 and CD54 biomarkers. One further piece of information we use within the model is market relevant data. So these are benchmark consumer exposures, which have been labeled as either high or low risk. Now I'll get to how and why we use those later on in the slides. But basically, we define a number of exposure scenarios, consumer market exposure scenarios, and label those as high or low risk. So these are basically based on historical experience. So, as I said, the SARA model is a probabilistic model. So the thing with the Bayesian statistical models is there's no real strong distinction between parameters and data. All quantities in the model are effectively variables or specifically random variables. The only distinction really that data is it just happens to be a random variable that you can measure or observe. And SARA model is built up from a network of conditional probability statements. To give an example of like this, the probability of sensitization HRIPT is basically modeled as a logistic function. And then conditional on the value of that function at a particular induction dose, what you would measure in a HRIPT is assumed to be an observation or a draw from a binomial sampling distribution. And this assumption, for example, allows you to account for sampling variability in the cohort of individuals who are present within a HRIPT study. The number of variables in the model is proportional to the number of chemicals in the data set we use to, which we fit the model to. Specifically, because we have 6 kind of study types in the model, each of those study types, or rather each chemical has 2 parameters associated with each study type for a total of 12. And what we do when we fit the model to the data is we will obtain a joint probability distribution over all the parameters, but specifically if we're interested in a particular chemical, we can look at the marginal distribution of those variables for the chemical. And we can start to ask questions such as what is the UD01 for a particular chemical, or what is its slope in the HRIPT, or what is its expected result in the DPRA, for example. One of the things that's a statistical tool which is used quite heavily in the model is this notion of is called partial pooling. So the idea here is that for parameters which pertain to variability, you assume that each chemical has its own variability in a particular assay, but the variability parameters themselves come from some distribution. And the reason you make that assumption is if you have an assay where you've only 1 experimental repeat, then you can still estimate the variability, but it is estimated by looking at variability or the distribution of variability across the rest of the chemical space. So I'm going to illustrate this concept using NAM data from the DPRA. So in this plot here, you're seeing observations of the maximum percent depletion in the DPRA for 5 different chemicals, indicated by the red crosses. So what you can see here is that for imidazole-lidonalurea, the variance in the observed values is quite small relative to the other chemicals. And then for formaldehyde, it's larger, for hydroxycitronelle, it's larger still. And then dihydrocumarin, there's only 2 observations, but it's looking similar to hydroxycitronelle. Now, on the right, phenylacetaldehyde, there's only 1 study. Okay, so in isolation, you would not be able to estimate the variability or the chemical-specific variability for that chemical. What partial pooling allows us to do is say, okay, so I can't estimate for this particular chemical variability in isolation. What I will do is assume that the variability parameter itself comes from the distribution of variable parameters for other chemicals. And what this assumption, and therefore, you know, the black line you're seeing for phenylacetaldehyde is the consequence of making that assumption. So in this case, you know, in the absence of repeat studies to say that this chemical would have small variability, the variance you get is in some sense an average of all the variance across all the chemicals where you can estimate it. This, we claim, is critical for not overinterpreting NAMs in the sense that if you only have a single experimental repeat of a NAM, you don't know a priori whether that value could be repeated or not under, you know, a second run of that test. So the SARA model, in the absence of that information, will assume basically that it will be as variable as any of the existing chemicals in there. And that effectively acts as a lower bound for the amount of information you will draw from that particular NAM result. And this kind of structure is applied for all the NAMs in the model and the local lymph node assay, and the slope parameters in the HRIPT. So it's a particular type of modeling technique which we use ubiquitously in the SARA model. The other major part of the model is if I know, for example, you know, once I've got estimates of, say, the average result in the particular NAMs, I need to be able to relate those back to the UD01. So the model assumes correlations between the NAMs, or at least correlations between the expected results in the NAMs and the UD01. And those correlations, essentially, it's a multivariate regression. But what's kind of a little bit novel about this is we assume a multivariate normal distribution to describe the correlation between the errors in those correlations. So specifically, if you've got 2 NAMs like the USENS and the HCLA, where they are, if one is wrong, the other one is likely to be wrong too. The errors when you're mapping, you know, from the, you know, when you're trying to go from the results of those NAMs to an ED01, because the errors are likely to be correlated, you don't want to overinterpret. You know, you don't want to count the error twice in some sense. And so, what we do in the model is try to ward against that by trying to understand the correlations, or at least the correlation between residuals and the regressions between the various tests. Okay, so I'll say the target inference is UD01, and for the current SARA database, which is about 80 chemicals, these are the estimates you get. Now, the width of these intervals, so these are 95% centered intervals of UD01 distribution. The thick line is a 50% interval. The variance in these distributions is variable. Some distributions are quite tight, some are quite uncertain, and this reflects the fact that we've got a heterogeneous data structure for the data set underpinning the SARA model. Some chemicals have lots of data, including lots of human data. Some basically just only have NAM data. And so your uncertainty is a function of the amount of information you've got to estimate potency. And this is why you get this variable variance in all the estimates within the data set. So one of the key things we want to do with the SARA model is that if you want to make a risk assessment prediction, you can do so with any amount of data. So, and this is what you're kind of seeing here. If I have just a single BPR array, I can use that within the model for a chemical and get an estimate of VD01. However, if I also have a keratin sens and a HCLAT, maybe a local lymph node assay, I can also use those. I can also use repeat numbers. So if I might have 3 BPR arrays and 1 keratin sens. And the model is designed such that you could use any variable amount of data. It will try to give you a level of precision on the estimate of VD01 appropriate to the amount of information you're given it. And typically, more information is better because you'll get a more precise estimate of VD01. And this makes it flexible. So as a DA, you don't require, for example, a fixed set of NAMs to input them. More is better, basically. Okay, so this is a measure of potency. So, but of course, this on its own, it doesn't answer the risk assessment question. What we do to approach this is we define a number of what we call benchmark exposures. So these are market exposure scenarios, which all exist at the moment, and they have been labeled as high or low risk for induction of sensitization, induction of skin allergy. So the idea here is that we're going to benchmark margins of exposure with respect to true risk classifications, which are established based on historical experience. So a number of chemicals within the SARA model have been have these exposures defined. There are multiple exposures per chemical. Effectively, what we do is for those exposures, we'll calculate a margin of exposure, and we introduce some model structure which maps that margin exposure to a probability of the binary risk classification. So the risk classification is either low or high risk. And there's model structure to effectively basically work out what the probability of that is given the margin of exposure. So what we claim here is that this moves away from the traditional approach of using uncertainty factors. Given a margin exposure, you might say, well, I'm happy if my margin exposure is above some threshold. We say, okay, let's, but of course, what that threshold should be, maybe somewhat uncertain. So what we say is let's use a data-driven approach. Let's define a bunch of things which we know are either true or high or low risk, and let's work out, from the margin exposure, how big it needs to be effectively to be confident that you're in this kind of low risk space. Retrospectively, of course, you could go and then work out a safety factor from this, but essentially the idea of this is that we could work out safety factors using a data-driven approach based on historical experience. This is what we're trying to do with the SARA model here. The paper published this year was essentially trying to be an evaluation of this model. So what we're going to do is try to evaluate with respect to these benchmarks, but the number of benchmarks is relatively limited currently. So typical splits of, say, a training set and a test set, it's not really practical given the limited number of them. So what we've done is use what we call leave one chemical out cross-validation strategies. So the idea is you leave out the risk classifications for a particular chemical, you refit the model, go and calculate the probability of the exposure of concern being low risk, and then do that for different sets of data for that chemical. So, let's do that using only in vivo data for the chemical. Let's do it using only NAM data. Let's do it using all available data for the chemical. And these have been, and then you get the probability for each of each exposure being low risk, and you compare that against the classification that you held out. And essentially what we tried to do in the published paper this year is demonstrate that the probabilities you get are calibrated. So calibrated means that if the SARA model is saying this exposure is low risk with a probability of 0.95 or 95%, then in reality there's only a 5% chance it's high risk. Okay. So calibration of probabilities when we're talking about probabilistic risk assessment is not necessarily guaranteed. Okay. And so our evaluation of the SARA model has been focused around trying to build confidence that the probabilities we're getting from the SARA model can be considered calibrated. What you'll see in this plot is if the black lines were falling outside this grey interval, that would be evidence that they are not. That the black lines are inside the grey intervals doesn't prove that they are calibrated, but it gives us some confidence that they are working correctly so far. So in conclusion then, so probabilistic model to quantify associations with explicit model structure to represent uncertainty and variability between historic in vivo data and NAM data, relevance and sensitisation, that's been built, takes into account variability in all data sources, we claim, provides a human relevant hazard-based output, which is called ED01, but also, given some exposure of interest, gives you a probabilistic, gives you a probability of that of the classification that exposure can be considered low risk, and it's been evaluated with respect to whether that risk metric can be considered calibrated. Next steps, we want to include me-too assays. So kinetic DPRA, we want to get in the model, we want to get a me-too assay for the keratinous ends, so something like the loose ends in there. One big critique of the current version of the model is the number of benchmark exposures is quite small. So we're proposing to work with dermatology clinics to identify further product chemical combinations that have some prevalence of people turning up in clinics as a result from. We want to explore more novel NAMs as predictors of skin sensitization potency. So, for example, NAMs focus around measuring the induction of oxidative stress, for example. It is hypothesized by some within Unilever that they may be useful for predicting skin sensitization potency. But we also want to bring some in silico tools into this as well. So in silico, predictions of reactivity, for example, derived from chemical structure, we would like to incorporate some of that, some of those tools into the model. So just some acknowledgements. Obviously, there's a large team at Unilever that has been involved with this work, and various collaborators outside of Unilever. So thank you for listening.
Thank you so much, Joe, for this very detailed illustration of how you deal with variability using modeling tools. And as Miriam was indicating in the chat box, this is a project that is currently on the test guidelines program work plan led jointly by the UK and the US. So the WNT will see that coming their way very quickly. So guess what? It's 2:15. It's the end of this webinar. I thank all of the speakers today very, very much for providing lots of resources for further thinking and reflection of the WNT in preparation for the workshop that will take place in December. And we have a couple more webinars to go. The steering group for the workshop will also soon be getting together to start shaping the agenda of this workshop in December. And the dates for our next webinar is not yet fixed, but you'll hear from me hopefully very soon on that. So with that, I thank everyone for their attention, and I wish you a very pleasant day, evening, and talk to you another time. Okay, bye.
Thank you very much.
Bye-bye from Baltimore.